Welcome to this video on metallic materials for additive manufacturing, focusing on alloy families and powder metallurgy. This is a comprehensive guide for researchers. In this video, we will explore the critical intersection of metallurgy, powder production, and laser powder bed fusion processing. Our learning objectives include understanding weldability in AM, mastering the microstructural evolution of key alloy families, and exploring powder metallurgy standards. Part 1 covers weldability and AM basics, examining the fundamental mechanisms that dictate how alloys behave during additive manufacturing. Weldability has evolved. While traditionally defined by success in welding specific structures, in AM, it translates to the ability to survive rapid thermal cycling without cracking. AM processability is unique. Not all traditional alloys work well in 3D printing, as wide freezing ranges can lead to cracking. Successful AM alloys often require specific design considerations. Solidification dynamics are key. Factors like thermal gradients, solidification velocity, constitutional supercooling, and epitaxial growth define the final microstructure of the part. Defect mechanisms include hot tearing, cold cracking, and porosity. These challenges arise from thermal stress and energy imbalances during the laser fusion process. A fundamental precept of AM metallurgy is that additive manufacturing is essentially microscale welding with macroscale thermal complexities. In Part 2, we move on to titanium alloys, the essential workhorse materials for both the aerospace and medical additive manufacturing industries. T6 ELI 4 volts is the most widely used titanium alloy. Its high strength-to-weight ratio and corrosion resistance make it ideal for optimized aerospace and biomedical components. We distinguish between standard grade 5 Ti64 and grade 23 ELI. The extra-low interstitial version provides the improved ductility required for fatigue-critical applications. Phase transformations are critical. Rapid quenching in PBF processes leads to the formation of brittle alpha-prime martensite, requiring post-built thermal processing. Cooling rates in laser powder bed fusion can reach 1 million Kelvin per second, trapping the material in non-equilibrium states. Finally, post-processing techniques like stress relief, mill-annealing, and hot isostatic pressing are used to optimize the microstructure and ensure component durability. This slide details the mechanical properties of Ti64 in various material conditions, comparing as-built, stress-relieved, and HIP process states against raw references. Now we transition to Part 3 of the video, where we will explore nickel superalloys, focusing on their extreme temperature performance and precipitation kinetics. Inconel 718 and 625 are the most prominent superalloys in additive manufacturing. They are prized for maintaining integrity under high heat in aerospace and nuclear applications. The strengthening mechanisms differ. IN 625 relies primarily on solid solution strengthening, while IN 718 uses controlled heat treatments to precipitate intermetallic compounds. Understanding precipitation kinetics is essential. Phases like gamma prime and double prime provide strength, while sluggish kinetics allow for welding before hardening occurs. We must also manage cracking phenomena. Solidification, strainage, and liquation cracking are significant risks that require careful process control. This table provides a reference for the technical specifications of IN 718 compared to IN 625, highlighting their different material capabilities. A critical constraint for Inconel 718 is the 650 degrees Celsius thermal ceiling. Above this, the strengthening precipitates transform into a brittle delta phase. Moving to Part 4, we will examine aluminum alloys, discussing lightweight structural applications and the science of grain refinement. LC 10 megagrams is the standard choice in powder bed fusion. Its near-eutectic composition helps suppress hot tearing, and magnesium additions allow for precipitation hardening. Printing aluminum comes with challenges, including high laser reflectivity, oxidation sensitivity, and high thermal conductivity, all of which require specialized process parameters. Innovation in alloy design, such as Scalmalloy, has introduced scandium and zirconium to promote heterogeneous nucleation, effectively eliminating hot tearing issues. Grain refinement is critical. We aim to move away from undesirable columnar growth toward equiaxed grains to improve the reliability of printed aluminum parts. This comparison table outlines the performance and suitability of various aluminum alloys used in modern additive manufacturing. Finally, we introduce Part 5, which explores advanced steels, ranging from ductile austenitic grades to ultra-high-strength maraging steels. We begin with 316L stainless steel. It is an austenitic alloy highly favored for its exceptional corrosion resistance and ductility, making it a reliable choice for diverse applications. Next, let's examine 17-4 pH, a precipitation hardening stainless steel. Its unique ability to balance corrosion resistance with high strength makes it ideal for medical instruments and aerospace brackets. Maraging steels, like 18Ni 300, are notable for being virtually carbon-free. Their ability to remain ductile after building, and then harden significantly during aging makes them exceptional for high-strength needs. Working with tool steels like H13 presents challenges. Their high carbon content often leads to cracking during printing, requiring careful management through methods like baseplate preheating. A key concept here is the carbon equivalent threshold. Generally, keeping the carbon equivalent below 0.4% is vital to maintaining weldability and preventing cold cracking in PBF processes. In this next section, we look at refractory and precious metals. We will explore how to push the thermal boundaries of laser powder bed fusion with these exotic materials. Tungsten and molybdenum have extreme melting points and unique brittle to ductile transition temperatures, which necessitate specialized processing techniques for radiation shielding and furnace components. Precious metals like gold and platinum present challenges due to high reflectivity and thermal conductivity, often requiring specialized green lasers to ensure stable melt pools. These specialty materials have diverse applications, from luxury watch cases and bespoke jewelry to critical medical implants and aerospace components. Now, we turn our attention to powder production, the critical step of creating the raw feedstock required for high-quality additive manufacturing. Gas atomization is the most common industrial method for producing AM powders. By using inert gas to disrupt a liquid metal stream, we create the spherical particles needed for PBF. Plasma atomization and the plasma rotating electrode process, or PREP, offer alternative production routes. These methods prioritize high purity and precise particle sphericity. This chart compares these various atomization techniques, helping to illustrate which production method best suits specific alloy requirements. Finally, we conclude by discussing powder characterization. Properly assessing feedstock is essential for maintaining quality control and achieving consistent results. Understanding particle morphology is key. Spherical powders are essential for flow, while a calculated blend of particle sizes improves packing density during the printing process.